You gotta defrost your freezer today. Yep, I can understand that. All right. So, Austin, Ryan, did either of you have any questions from any of the previous? Okay. Summer, welcome. Did you have any questions on anything? Okay. Yep. There was one due last. Okay. So there was one due Wednesday and then Thursday, Friday. And then there's. Yeah. Okay. Well, if you run into problems, just hit the ask my instructor question or ask my teacher. I forget what it is. And that'll shoot me a question, okay? In the problem, Ryan, you do it all the time. Okay. All right. Okay, so today we're going to work on 6.4. 6.4 is perfect square trinomials. And the difference of squares. All right, so all right. Looking at these 5 trinomials. What do they all have in common? Okay. True enough.
They're all the number times the number, same number, to get the last coefficient. Actually, half of the middle number is double the.
Okay, go with that last one again. What are you trying to tell me about the last one? The 25, the 9, the 64, the 16, the 49?
The number is times itself twice.
Give a different way of saying that. 25 is not 25 times itself.
5 times 5.
Ah. Do you know what those are called?
Square root?
Not square root, but
They're all divisible by each other.
no, they're not divisible by each other.
Square functions?
They're all square numbers. All of these ending numbers are all perfect squares. 25 is 5 times 5. 9 is 3 times 3. 64 is 8 times 8. 16 is 4 times 4. 49 is 7 times 7. So all of these C values all of those C values are all perfect squares.
And B value is sort of odd in half. It's the number you use to square.
B, B is what?
10.
Now, how did we get a 10 here?
You wrote it with a pen.
I did write it with a pen, a black pen. But how does this 10, how can I work that in with a 25? In the same way that a -6 can work in with that 9.
5 plus 5 is 10. 5 times 5 is 25.
Okay. So the B value is all right.
Look at what you're trying to
You,
say.
do you get what? Can you see the pattern even if you can't quite describe it?
Oh, yeah.
Okay.
5, 3, 8.
Yeah, and how does a 5? 5 is how much of this 10?
Half.
Okay. So this B value, and what did we do with the 5 here? We had to square it, right? Okay. So how do I get a 3 out of this 9?
Divided by 3.
Yeah, but what's the opposite of a square?
Square
So if I take the square root of 9 and then I take the square root of 64. What's the square root of 64?
8
And then how do I get to 16?
times 2.
Is it okay if I say double it instead of times 2? So by that, the square root of 16 is 4. And then if I double it, that gives me 8. The square root of 49 is 7. And if I double it, that's a -14.
Yeah.
Okay? This is the pattern of a perfect square trinomial. These are recognizable because this first term will be a perfect square. The last term will be another perfect square. This middle term will be the perfect squares multiplied together and doubled. Now, I say it this way because there won't always be a 1 in front.
Could you say the perfect square is multiplied by itself?
No. Cannot say multiplied by themselves. All right. Here we go. There are two patterns. The first one says you have a perfect square to start, you have a perfect square to end, and the middle term is the square root of each multiplied together and doubled. Or, as my algebra teacher way back when in 1984 said, square multiply double square. Notice that this is a positive sign. So when factored, you will get a plus b times a plus b, or a plus b squared. Similarly, a squared minus 2ab plus b squared follows the pattern a minus b times a minus b, which is an a minus b squared. again, you see the same pattern. This first term is a square. We subtracted the multiply double. And the last term is a square.
Can you remind me again, you know how a minus b squared, remind me why you don't do a squared minus b squared?
Because you have to FOIL, you're squaring the entire thing. So a minus b squared means a minus b times a minus b. You cannot distribute that squared inside the parentheses. You're literally writing the parentheses twice.
I always get confused why.
You're not the only one, but you've got to break the habit.
What if there was a squared minus b squared parentheses squared?
Then it would be a squared minus b squared times a squared minus b squared. That squared means you're writing the parentheses twice, not distributing.
So when do you multiply what are those numbers called? The powers.
The exponents?
Yeah.
If there was no plus or minus in here.
Oh, okay.
It's the plus or minus that messes up that sort of shortcut for you.
Okay.
Okay? Okay, let's try a couple. All right, example 1. We're going to factor this guy. X squared plus 18x plus 81. All right. X squared is x times x. Is 81 a perfect square?
Yeah.
So this would be 9 times 9. Is my middle term 2 times 9 times x?
Yeah.
So I've multiplied each of the square roots together and doubled it. So I've got a square, multiplied, doubled, and a squared again. Yes? So this follows the pattern. X plus 9 times x plus 9, which is x plus 9 squared.
So we're not really solving them anymore. We can just figure out the pattern right away and
You can't, yeah, for perfect square trinomials, you can figure out the pattern right away. If you cannot, or if you miss it, I would just like to point out, right, let's say you don't see the pattern, and instead you say, okay, we've got to multiply to 81 and add to 18. Right, so the previous method we've done. So you don't see the pattern, and instead you do x squared plus 9x plus 9x plus 81. You pull out an x, you pull out a 9, Do you see how you get the same answer anyway?
Yeah.
But
Ryan.
the very top, the 2 times 9 times 8, you're just getting, or x, you're getting the x from A, the 9 from C, and then just double it for B.
Correct.
Yeah.
And all I'm doing there, by taking the x from x squared, the 9 from 81, multiplying it together and doubling it, is I'm just checking the pattern to make sure that that is an 18x like it says.
So, never mind, I'm going to wait.
Okay, if that wasn't 18x, I couldn't use this pattern. I'd have to look at a different way. Okay. Do you recognize this as x times x, a perfect square? And 100 is 10 times 10, another perfect square. If I multiply each one of those square roots together and then double it, do I get that middle term? That means that this trinomial fits the pattern. And it will factor into x plus 10 squared. Okay. Let's try a little bit harder.
That's what I was going to ask.
Okay. Okay. So, is 4x squared a perfect square? Is 4 a perfect square?
Yeah.
So to get 4x squared, I could do 2x times 2x. And 25y squared is 5y times 5y. So I've got a perfect square to open, and I've got another perfect square to close. If I multiply 2x times 5y, and then I double it, do I get 20xy? That means that this is a perfect square trinomial, and it will follow the pattern a plus b times another a plus b, which is 2x plus 5y squared.
That's where you're getting A plus B plus B.
Yep, that's the pattern.
Or is it Isn't it actually a plus c?
No, this is a squared. It's a slightly different. Never mind. No, no c. No, don't worry about the c. Okay. Looking at the first term, is it a perfect square?
Yeah.
4x times 4x. Looking at the last term, is it a perfect square?
Yeah.
We forget about this one, which is why I wanted to do it. It is 1 times 1. It is a perfect square. Now, if yeah?
I'm just starting myself.
Okay. Now, if I take each of those roots, 4x times 1, and I double it, do I get the middle term?
Not the sign.
It's not.
But the sign I can switch. So I can, so that's fine. That just means that it will be not a 4x plus 1, but a 4x. Yeah. Now, example 5 is going to use the same patterning, but it's asking you to factor completely. The idea here is that you recognize you could take an x out of each term. And then you recognize that 49 is a perfect square. So you've got 7x times 7x. That 1 is 1 times 1. That if I multiply a 7 times 1 together and double it, I will get a minus 14.
So when a is just x squared, there's no number. Um, and it's a perfect square trinomial. Are B and C both going to be squares?
Say that again, Ryan.
Never mind.
No, just say it again.
Well, because when there was no number in front of the exponent, it was the half of B.
Yeah.
But now
Yeah, if there's a coefficient on the lead, so like when there's a 49, right?
yeah.
You've got to be careful because it's not always just going to be half of the C value. You've got to take all of them into consideration. So if, for example, this was a 9x, let's say cubed, plus, let's say 12x squared, and let's say plus 16x. I think that one will work. Okay. Do you recognize, first of all, that you could pull an x out of each one of those terms? So we always want to do the GCF first. Then I recognize this first term is 3x times 3x. And 16 is 4 times 4. Now this middle term should be 2 times 3x times 4, or 24x. So it should be double the square root from each, from your A here and from your B. Is 12x 24x? So this does not fit the pattern. And I cannot use it. On this one, I am done now. This is all I can do for factoring. Does that help some, Ryan, or confuse?
No, I'm good.
Okay. Summer, you all right with that?
Yep.
Okay. Austin, anything from you?
No, I'm good. Thank you.
Okay. All right. So that's a perfect square trinomial. We still have another pattern to go over. And this pattern is called the difference of squares. So remember when we were multiplying in the last chapter, and if we had, say, an x plus 5 multiplied by an x minus 5, we do the first, and that would get us an x squared, right? we do the outside. And that's going to get us a minus 5x. We do the inside for a plus 5x. And then we do the last for a minus 25. And when the signs are different like that, one is a plus, one is a minus, the O and the I, the two middle terms, would always cancel each other out, leaving us just an x squared minus 25. Or a square minus another square. AKA the difference of two squares. The pattern says if you have an a squared and you're subtracting from it a b squared, this had to have started, right? We've got an x squared minus 25. We had to have started with an x plus 5 times an x minus 5. Some people like to use the F's and the L's from the FOIL. It just helps them to sort of visualize it as they go. And if that's your preference, that is absolutely fine. So let's try a couple of these with the pattern and see how quickly it catches on. So we're going to factor x squared minus 9 . This is the difference of two squares. X squared is x times x. 9 is 3 times 3. So my factors here would be an x plus 3, x minus 3.
Answer, can we write it as, oh, never mind.
Right? I get it. You look at that and you want to sort of condense it like we did the last one, but we can't because they are different factors. Right. We had to factor 16 minus m squared. 16 is 4 times 4. M squared is m times m. This is the difference of two squares. So I have two different factors for minus m, for plus m. All right, so now we have n squared minus 45. N squared is n times n, but is 45 a perfect square?
No.
Since it is not a perfect square, the pattern cannot be used. And this is prime.
And if you start using decimal,
Again,
We won't.
some decimals are perfect squares. But that's not my intention to catch up on that, at least not on any kind of test.
sounds good.
Here we have a b squared plus 4. B squared is b times b. 4 is 2 times 2. However, this is not the difference. And because it is not a difference, this is prime and the pattern cannot be used. Okay, so a couple of things to watch out for when patterning. The pattern has to match. It can't almost match. So in these last two examples, this was not a perfect square. So I cannot use the pattern and I have to call it prime. In this example, it's a perfect square at b squared and it's a perfect square at 4, but it's not the difference, it's the sum. And because it is the sum, I cannot use the pattern, and the answer here is prime. It will not be factored.
So, example, on the other side that we did, the 9x third plus 12x squared plus 16x, that one's also prime.
This is not prime because I was able to factor out an x.
Oh,
If they had just given me this to factor, this we would have said was prime.
okay.
But because we were able to take an x out initially, this problem was not. Okay? All right. Yes, sir.
On that, well, on that last one you're just showing, if you're just trying to factor it, can you do it two ways? Times c, and then because the number wasn't 1, then you figure the numbers add up.
Are you doing this one?
Yeah. I mean, can you use both the two things we've learned to factor? Say like 6, if it was plus 12, if you, or plus 6 and 2, or I don't know, Ryan.
Okay. So, Ryan, if you can use that A times C method here as well,
Yeah.
but then you're going to have to find multiply to 144, and it's got to add to 12.
Yeah.
I get 144 from 9 times 16, right? And basically what you're going to find is that there's not a number. There are no numbers that multiply to give you 144 and add to 12. And so at that point, you would say this cannot be further factored, and you'd be done.
Okay. And then the first day, when it was just x squared, so it was x squared plus 12x plus 16, we were trying to find numbers that equal 12, but when you multiply them equal c.
Well, it's still a times c, it's just that your a is 1. So you can still do 1 times 16. You can use the same method there.
That's why I was just wondering if it, like, the last couple of days, if we were kind of doing the same thing.
Yep.
Yeah.
We're doing the same thing over and over in all different kinds of iterations. Yes, sir.
Yeah.
Okay, but today we've got patterns, so today's a little bit different.
Yeah.
25x squared minus 49. Okay. So, is 25x squared a perfect square? 5 times 5 is 25. X times x is x squared. Is 49 a perfect square?
Yes.
And is that the difference? So we have here the difference of two squares, and we can write this as 5x plus 7 times 5x minus 7.
So a square that's 7x and a square that's 7, that's different, right?
Yes.
Yeah.
So here I've got 4x squared minus 25. 4 is a perfect square. X squared is a perfect square. This would be 2x times 2x. 25 is 5 times 5. Whoops, I didn't do that in my red pen. And this is indeed the difference. So I can use my pattern here to say that this is 2x plus 5 times 2x minus 5. It's worth mentioning that if we rewrite this as 4x squared plus 0x minus 25, I can use that AC method and say, okay, let's multiply to a negative 100 and add to 0, because I don't have an x term, I can do that as 0x. So what two numbers would multiply to give me a negative 100 But when I added them together, I would get a 0. Well, 50 times 50 is not 100. So I wouldn't want a 50. You're right that the signs would be different, one positive, one negative, but it wouldn't be a 50. I could, however, use a 10, a minus 10, and a plus 10. I'll pull 2x out of the first two terms. Oops. And I'll pull a positive 5 out of the last two terms. And I get the same two factors that I did by recognizing the pattern. I'm just saving some work.
Yeah.
Right? That's the whole idea with the patterns, is that they sort of end up being little shortcuts. You will also get some problems where you have to factor completely. Oops. Notice that in both of these terms, I can take out a 4 and I can take out a y. And that will leave me with an x squared minus 25. Perfect square minus another perfect square. There we go.
That was my last sheet of paper in my notebook, so it's done now.
Well, we're done with 6-4, which means
Alright, so
we're done for the week.
Can't believe it's already Thursday.
I know.
I mean, like, I don't back of the days anyways, but like, guess it's okay.
All right, let's see. What do we want to do here? All right, and that means we're done